right, thank you. It's good to be here. My name is Xing, also on the right. Michael Gruninger is my PhD thesis advisor at the University of Toronto. So this paper is based in large part on a section of my PhD thesis. The title is The Complexity of Partial Order Plane Viability Problems. What? Thank you. So this is the title. We know that partial order plane defines a set of actual events associated with partial order constraints on their occurrences. So a partial order plane corresponds to possibly many different ways of linearizations. If there exists at least one of them that would achieve a condition, a propositional atom, we say that this partial order plane is viable for that condition P. So this is viability problem. It is known to be NP complete. But the contribution of this paper is that we managed to identify a set of different constraints that contribute to this intractability. So here is the outline. It can be divided into three parts. First, we would present the results. And it turns out that the viability problem is closely related to the well-studied temporal projection problems. So in the second part, we would address these relationships and give a historical remark regarding the motivations that motivated us to do this current research. In the third part, I would give some explanations on the NP hardness part, like the polynomial time transformation for the proofs. And finally, I would summarize the work. So part one starts with definitions. The definitions is mainly on event systems for historical reasons. Let's see what is an event system. A causal structure defines a three-tuple P, a set of conditions, that a subset of them defines a state. So T is a set of event types. Okay, so events like the change state from the current one to the next one, guided by R, the causal rules. So an event type has preconditions which would guarantee its applicability for a given state, and added list and deleted list would defines the change, the application of the event to the state. On top of the causal structure, we could define event system. So with PTR, we also have E, actual events, all right? So the difference between T and E is that we might have a pickup in T, and we might have multiple occurrences of pickup, first pickup, second pickup, on actual event E. So the partial order is applied on E instead of T, and an initial state I. So from these, we can actually define a set of CS, complete sequence, which is all linearizations of E with respect to partial order O. Okay, so this is a generic definition of event system. We can define restricted cases. For example, for almost simple event, it is required that the size of the state is bounded by a fixed number. It can be reduced, but it cannot be expanded. For simple event system, this state size is bounded to precisely to 1, all right? So when the event system is at least almost simple, the cause and effect relationship can be depicted as a cause and effect graph, all right? We know that given the state, an occurrence of an event is applicable to occur if its preconditions are satisfied in this current state. We can generalize this admissibility from one actual event to a sequence of events. So the definitions is here. On top of these admissibility definitions, we can move on from the set CS, complete sequence, to ACS. In addition to the constraints of O, it is also required that the admissibility constraints are satisfied. We can define planning and plan with respect to event systems too. So on top of the causal structure, we define the initial state and the goal state. A plan is actually an event system without the initial state explicitly specified. All right, so given a partial order plan, given an event system, the plan viability problem is defined as checking if there exists a linearization in ACS which would achieve a given condition P. All right. So now I'm going to give you an example to facilitate the easier understanding of these definitions. The basic scenario here is that I would like to drive my car into the garage. There's a passenger in my car, and I wanted to drop off her before I drive the car into the garage. So the conditions P here is that the garage door is open and closed. The car is in the garage and out. Passenger is in the car and out. The T has three different event types: open the garage door, drive the car into the garage, and drop off the passengers. This is the causal rule, pretty intuitive. And we assume that each event type has exactly one actual occurrence. So E is the same as T. There's only one partial order. It is required that I have to drop off the passenger first. And the initial condition is the door is closed, car is out, passenger is in the car. So P, T, E, O, I, and R, okay? This defines an event system and a partial order plan, right? Now, like all of the linearizations are presented in this table. Each row corresponds to one linearization. But only from this table, we look into three different properties: the ordering constraint, admissibility, and wholeness of particular conditions. In this case, door open after the execution of this partial order. We use the buttons, like black button and white buttons, to indicate it's true or false. So it turns out there's only a subset of them, like are members of the complete sequences. And only two of these three actually are the members of admissible complete sequences. This is two of the possible ways, linearizations of these partial order plane. So we would like to see that given these partial order plane, given these two candidate linearizations, if D open is viable for this plane. For this particular case, it is not possible because we have this white button here. However, if we look at the D close, it is viable. It needs to be remarked that it's not necessary that all of the linearizations would achieve D close. At least there exists one, it is viable. So this is the definitions and example of partial order plane viability problem. It is known to us that the problem is NP complete. But actually, we are able to identify 5 more restricted cases. 3 of them are intractable, 2 of them are tractable, which are summarized here. Intractable result first. If the event system is almost simple, viability is still NP complete. If it's simpler, NP complete. If it's almost simpler, whereas the cause and effect diagram is a DAG, it's NP complete. However, if it's simpler plus DAG, it is polynomial time solvable. If it's almost simpler, and whereas the set of O partial order is empty, it is polynomial time solvable too. So these 5 results are summarized in this figure. So all of these rounded rectangular stands for a problem, and it's restricted cases. And energy here is that, it's like set, 3 set, and 2 set. Okay, it is divided into 2 parts, left part and the right part, with or without partial orders. The 2 problems on the top, like their NP completeness, are drawn from literatures, and for the 5 results below are ours. You can see there's a clear boundary line here between intractable and intractable. There are the arrows linking them, like pointing to restricted cases. So in this case, there are at least 4 arrows across the boundary, but each arrow actually captures a particular kind of constraints. For example, we know that at that case, like it's intractable, NP complete, but if the event is in addition simpler, then it becomes polynomial time solvable. So this arrow is a reflection that the size of the preconditions actually contributes to the intractability of these problems. All right? So on top of, all problems on this page actually are admissible because this is a viability problem. There's another one like in the air with the admissibility constraints relaxed. It's stack, simple, and inadmissible. Like from the literature, we know that this problem is also NP complete. So it points to polynomial time solvable, which captures another constraint in admissibilities. All of these constraints that contributes to the intractability are summarized in this list. This slide and the previous one are 2 most important slides of this talk. Okay, so I'm not going to read through them one by one, but this one is derived. It's not directly drawn from that figures. Okay. Now we move on to the relationship between plane viability and the temporal projection problems. I would first give definitions of these 2 problems. I'm repeating viability problem for plane here. And this is the definition for temporal projection. Okay? It turns out that the only difference between viability and the traditionally defined temporal projection problem is that the ACAs is relaxed to CAs. Admissibility requirements is relaxed. So actually, we can call plane viability problem as admissible possible truth, and the traditionally defined temporal projection problem as inadmissible possible truth problem. I abused the logical sample equivalence, but okay. So they're actually possible truth problems, admissible and inadmissible. Okay, here, like the possible truth problems were studied in these 2 papers, Dean and Body, like in 1988, AIJ, and Libel and Backstrom in 1994, AIJ. So in paper 1, it shows that inadmissible possible truth and general case is NP complete. Paper 1 conjectures that for simple case, it's polynomial time solvable, but paper 2 actually found that this case is NP complete by proving more restricted cases. In paper 2, it also says that for admissible possible truth problem, for the plane viability problem, it is, again, like NP complete, which leaves a gap here. Like we wanted to know what is the complexity for these 2 problems. These 2 question marks like motivated our research. Actually, we managed to find that a dividing line here, NP complete, and a polynomial time solvable. So this one is the problem in the air, okay? And this is another dividing lines, but we took a much closer look at these dividing bound lines. Okay, so now like I would give some explanations regarding NP hardness proof. So this is the its transformation from the Hamiltonian parts with input node and output node known. So for this case, there exists a Hamiltonian part. So we wanted to transform some cause and effect diagram and an event system from these original diagrams. So the basic trick here is that instead of treating nodes as conditions, we treat them as events. All right? we split the nodes into left nodes and right nodes with an actual one point into it, and add some cleanup work. This is the initial state, and traverse are Hamiltonian paths. But these two needs to be traversed too. So we use these two to traverse that. This is basically the proof for the first NP completeness result. And we move on from almost simple to simple, but the problem here is that it's only almost simple because the initial state size is 3. So we have to reduce it from 3 to 1. But the problem is that we still need these two to be activated somehow along the way. So the trick here is that when this one is activated, it is used as a hub to repeatedly activate these two nodes. In order to do that, we add some more gadgets to solve the problem, and connecting them with this hub node. Here is the dynamics. From here, we travel through the Hamiltonian paths to get here, and then everything else follows naturally. Natural? Okay. So, all right. This is the third case. Like I cut off the edge 1.5, right, to make sure that this is a DAG. This is not only a DAG, it is isolated island. So here's the summary. Like the viability problem is intractable. We managed to find a set of different constraints that contribute to this intractability. We believe that this result might be helpful for planning heuristic development. This is pure speculation. And we deepen our understanding of the well-known temporal projection problems. The polynomial time transformation is performed on the well-known NP-complete direct Hamiltonian path problem. Here is the acknowledgement. The thesis, like Professor Beck and Macris are in this conference and was in my committee. Professor Mihai Solchansky from Ryerson University read an earlier draft of my thesis. We are thankful to the numerous reviewers. This work was completed when I worked for Professor Wojtek Miknowski at the University of Ottawa as a postdoc, sponsored by Untitled program. So this finishes my talk. I thank you for your attention.
Okay, that was on the spot as far as the timing goes. Oh.
So I was wondering, why do you think plan viability complexity has any connection to planning heuristics? Because there's been a lot of work in the past after Chapman's conjunctive truth criterion. There was a question as to whether it has any connection to actually developing heuristics for planning, and there's been work showing that it's not directly related. So I'm wondering, are you aware of that work, and do you really think, I mean, you can talk about complexity of, temporal event systems, but why is that directly related to heuristics for planning?
All right, so first of all, this is like the pure speculations. I have to be honest, because I personally myself do not develop planning heuristics. It's just like I come up with these results. I think they're nice, and my speculation is that they should be yes, but I think it might be helpful for.
Yeah, I think, I did not notice in your references any connection to model truth criterion, for example. So there's a whole bunch of literature around that, and people have looked at whether these kinds of reasonings would actually be connected to plan synthesis. You might want to look at that to see whether your speculations are still warranted. If they are, it'll be very useful.
Okay. So actually, like the plan viability problem, was explicitly defined pretty new in 2011 by Mewis, Beck, and Macris. So the problem is explicitly defined only recently, plan viability problem. So I think it's good following that result, giving some additional complexity results. and I thought that it might be helpful for, yeah.
Okay. I'm sure you all got lots of question marks in your head. Okay, let me make a command, unless somebody else wants to ask a question. So I'm bewildered. Okay. I mean, I was sitting here. I mean, why do you reinvent all those notations? I mean, could you please translate this into our language? I mean, like the event effect graph, I think is a causal graph.
Yeah.
What you call event is, I think, an action.
All right.
What you call admissible is, I think, an applicable action sequence.
Okay.
So why don't you just call them these names? I mean, I was sitting next to Carmel, who's been working on planning complexity since I was born, and he didn't understand what you're talking about. So this is an indication. I mean, please, if you want to make your work accessible to us, please frame it in our language, because like this is just next to impossible to understand what you're talking about.
All right.
I think this is basically what I got to say. Okay, so let's thank the speaker again.
All right. Thank you.